All right, so good morning, everyone. So as we mentioned last time, like today we will discuss, we'll go through quickly SAP training for like how to conduct pushover analysis. So pretty much I'll go quickly so how many of you like familiar with SAP? Like did something before? Okay, the rest didn't even open it. Somebody never seen it before? Never seen SAP or like?
We probably opened it, but never used it. Right?
No, but I mean like familiar, like with like if you
No, not
beam something like this.
It was never taught.
Okay, so this like as I mentioned last time, I hope you have done some quick training before we start today, because I can't go through each specific thing in SAP because this will need 4 or 5 lectures, and I don't have time. And technically, I'm not obliged to do SAP training, but because I know otherwise it will take you a lot of time and a lot of questions to conduct pushover analysis. So this is why I'm doing this lecture. So I'll go pretty much quickly, but then you have the lecture on YouTube, and then you can go through it. If you have any thing, you can pause, you can check it online. All right? Okay, so pretty much the example I'm going to do today is a 4-story four-story 3-bay non-twisting frame. And okay, I'm trying to model this thing, members and loads and all of these things. We'll try to guess some members while we are going when we try to model right now. So okay, so first thing first. So now we open SAP. You already have the educational version. All right, first thing, you start by doing a new model, and then you will get this dialog box, and then you will have to choose pretty much what you're trying to model. You can start from scratch by doing from a blank project, and then you start modeling points. Or since we know that we are doing a 2D frame, so this is a 2D model, then I can select this one over here, this template. For the, again, units, we are using kip and inches pretty much for what we're doing. So I'm using kip and inches from here, and then I'm using 2D frame. So then you will have to select the number of stories. Then after you say okay, you have another dialog box. You have to select the number of stories, number of bays, the story height, the bay width, and so on. So for here, let's stick with the story height and the bay width that you have right here, which is more or less, I think, are fine. 144, which is around 12 feet in height, which is okay. 288, again, double, which is around 24 feet, which is again okay. So I'll stick with those ones. Number of stories, I have 4. Number of bays, I have 3. But then again, we know that when we model 2D, in order to include the P delta effects, then we have to put the leaning column, right? So since I anticipate doing this kind of thing, then instead of doing 3 bays, I'll actually do 4, because I will have another bay right here. For the leaning column again. So I'll make it 4 number of bays. So okay, and then it tells me section properties and so on. So this will assign later, no problem. So I say okay, and then I get those two. Let me check something here. Okay. Okay, that's fine. All right, so okay, so you have like those two views, like 3D view and then a 2D view, which is the XZ plane. So okay, I'll close this one, the 3D view. I don't need it. I'm working in 2D. So here you go. You have your model. You have some elements like columns and beam and so on. And then you will start. The first thing you need to do. I start by doing the constraint or restraint, like pretty much the support. So I'll select the ones on the left here, those 4 at the base. So I select those 4 nodes, and then I go to assign. Pretty much, if you are familiar with SAP, you have like 2 main command dialogues: the assign and define. So you define something and then you assign it and so on. So I'll go to assign right away and then joint and then restraint. So I go to this one, and you have like you have to say like which degrees of freedom. You have 6 degrees of freedom. It's a 2D model, so 3 translation and 3 rotation. You can select those, or if you already have like those icons over here, so you can select directly, like if you want it like hinged or like a roller support or fixed support or a free point. It's up to you. So I'll use like the fixed, like, because this is what I'm trying to model here. So I'll say OK, and then if you look here, you have those fixed support. Here for this one, for the grid, for the leaning column, okay, this is hinged, that's fine. So I leave it like this. Then let's go again, like since we are still talking about like boundary conditions and so on. So if I look at like this bay, I need those things to be truss elements. Pretty much if I look here, like all those members are connected as fixed connections, all right? So if I need them to be hinged connections, all right, or like a plastic hinge, pretty much, 0 rotation, then I will need to introduce those hinges here for the columns and the rigid links, both. So this can be done easily, like if you have a truss member in general. So you select those again. So I select all those members, and then I go to assign, and then I go to frame, because this is a frame element, and then I go to release. This one, release. So if I select this one, and then I say I want to release the moments at the ends, at the start and the end of the frame element, which is pretty much M33, which is MX for us, the moment in the main direction, the strong axis direction, and M22 is in the weak direction, and then you have the moment like around Z, which is the torsion, right? So for here, like, okay, we care about M33, but just doesn't matter. We can release both of them, M22 and M33, both at the start and the end of the member. So I'll select those again. The torsion, you can only release it at one end, so I'll just select the start, it doesn't matter. Shear and axial load, no, we don't release those. We leave them because, again, like those members, the main idea is to translate the shear and the axial force to the lateral, to the main lateral force resisting system.
For the torsion, why you just release the start one?
Because this is what's happened. Like you don't actually you can do. Oh, okay, you can do it. But if you release one of them, it doesn't matter. You don't need to release the end.
Okay.
Because the torsion, like it does like warping stresses and so on. So pretty much if you release one of them, you don't need to release the other. But okay, it doesn't matter. Actually, like for the torsion and M22, we don't care because we are looking at the strong axis direction in 2D. So pretty much I only need M33. All right. And then I say OK or apply, it doesn't matter. See what's said? Like, because this, we can do this. So again, if I go to assign, frame, release, because I did like start and end, so it gives me an error. So that's why it has to be like one direction only. And then once you say OK, So this is what you get. Like this is like how it looks like when you have a release. So you have like those screen hinges at the end, and then the member like contracted a little bit. So this is how it looks like. So now I have hinges at the end and the base. That's fine. I'm done. All right. So next, I did all my boundary conditions. Then let's start defining the members, beams and columns. So I go to define. So now I need to start defining some sections. Pretty much we are using wide flange or I-shaped sections. So I go to define. I go to section properties. So I need to define a frame section property. So a frame section. You have other things like area and so on and reinforcement. So area, this is when you are modeling like slabs and things like this. Anyway, we are going to frame section. And then I will say import new property. You can add a new property and so on and so on. I'm importing a new property because I have a library for the wide flange sections. So I need to import those. So I click import new property. So it will tell me, okay, what's the material type? Steel. Okay, that's fine. If you want to define a new material, because okay, this steel that's defined here, it has some parameters like E, F, Y, and so on. If you want to modify those things, which for your assignment for sure you need to modify, because you have your own material now, then you can modify a new material. You call it like steel A992 or something, and then you start defining E and FY and any other parameters that you will need. So I'll just stick for steel for now. All right, and then it's an I wide flange section, so I click this one, and then it will give me like this browse dialog box. Like I need to select the library from which I'm importing like this section. So I think when you install the SAP, you will get like all this library. So I'll go to AIC14. This is the latest one. M, which is the modified version. So just select this one. So this is the latest catalog of sections. If you use like any other one, it won't be a disaster. But if you want to be specific, so I'll use this one. And then it will give me, okay, here you go. The material A992 FY 50, so 50 KSI is the nominal strength. If you want to make it 55, then you will have to define a new material. And then I'll scroll because I want to go to a W section. So you have many types of sections. So I have the W sections over here. So let's assume like here for those columns, I have like W24 by 146. In this one, I opened the metric, AIC14M. M stands for metric. So, okay, if we don't want the metric, because maybe cancel this one, import again. We need to close it, all of it. Okay, so define, frame section, import. Sorry?
Again, push the import new properties. Go there.
And
Cancel this.
okay.
And it has an import.
So okay, so
open file, sorry.
all right, yeah, that's fine. So I'll go with like AIC14 because this is the imperial units, so W24 or something. So again, this one. So here, okay, it makes more sense given the ones we're familiar with. So let's say W24 by 146. I'll select this one, okay. That's it, you have the parameters over here, the flange, the web, all those things. And then okay, that's fine, so I have it right here. Let's import a new one since we are here. So again, let's say W24 by 146, let's say here W24 by 103 or something. So W24 by 103. All right. Let's say for the beams, like I don't know, like W21 or something. So let's go W21, maybe W21 by 57. All right. Okay. So that's it. I have 3 sections. For the columns, like assuming I have different columns. For the beams, you should have like different beams maybe for different floors, but let's just assume it's only one beam for now. And then, okay, but then I need to define another section. Because for those ones, for the leaning column, we said like for the leaning column and the rigid links, I should have like some kind of section with very large cross-section area, axially rigid, right? So we need to define a new section. For this, you can do, you can import a new property. You can choose an I section with a very large weight. So something like 14 by, like, I don't know. You can come here, you can select maybe something like W14 by 730. This is a pretty massive section. You can do this. And then even after you select this one, you can modify it if you need it, like even to have a bigger axial stiffness. Let's say if I select this one, for example, see it's really stocky if I look at the section. If I need to like just to be safe, I can come here to set modifiers, and then I go for the cross section. So this is to modify the property. Maybe I make it like 100 times more. So when the program is working like in the background and establishing the stiffness matrix, it will come for this term like EA over L, and then it will multiply by 100. All right. So this is like stiffness modifier. I can do this, for example, if I'm doing like composite action, maybe I can come for like the M, moment of inertia I. If I'm doing like something like concrete, like cracked section, maybe I do this like 0.4, right? 40%, so that I modify this component like EI over L. So this is like the modifiers. You can do this here, all right? So, okay, you can do this. We can do it. Okay, that's fine. Or you can add a new property. Something like add a new property. You can do something like, I don't know, a tube or something, and then you make it like something really, really thick. Okay, it has to be less. 3 T-flanged. Okay. Oh, this is the thickness. Okay, so it's like 6 by 6, and then the thickness is 2. Something. You can do something like this. But then again, like you don't just do it. You have to go to the properties and you check the area. And pretty much when we are doing something axially rigid, it has to be at least like 100 times more than the other section you have in your model. Okay, so if I have like the maximum area like here for W24 by 146, I don't know, like 90 inch square. So this one, it has to be like 9,000 or something. Anyway, okay, so we defined this thing and we defined all our sections. Then, okay, and then I start defining the section. So again, we said like the columns. Let's say I have all the columns up till this point. I have like some kind of splice and mid height. So those are all W24 by 146. So I need to select and then assign. But here I have this one, it's one element. So I need to divide because I have a splice. So what you can do, you select those 4 elements. And then you go here to edit lines, and then divide frames. And then you say, okay, divide into specified number of frames. Number of frames, I say 2, divide into 2. The ratio, it's 1, because it's in mid height. And then, okay. So now I have a point here now in the center. So then again, I select my columns, and then I go to assign frame section, and then I say okay, W24 by 146, and then okay. And then I go to the rest of them, the one that's at the top, in the 4th story and 3rd story, I select those, and then again assign frame section W24 by 103. For the beams, okay, they are all the same, I assume, just to be quicker. So I go here, okay, assign frame section, we said W21 by 57, so okay. So now I have my sections. I still need to assign those, so I select the leaning column and the rigid links, and assign the rigid section that I said, like frame section, the W24 by 730 modified by 100 times the axial stiffness, so that's fine. Okay. After you do it, you need to double check, because this is very important that everything is correct. You can do, I think, like here, and then if you go to okay, so now you have the label for the section, it's already shown. If you want to okay, where was it? I think it's don't remember, there was like this option, don't know if somebody remember, like to show the sections. Extrude. Where is extrude? Do you see it? Extrude. Okay, they changed it because it used to be on the left side. Okay, so yeah, if you look at this, you can see the sections. So W24, okay, it's the same depth pretty much. If you go like a 3D view, so you can pretty much see it. So the columns are pretty much the same depths, that's why they don't change. That's fine. Those I see them again the same depth, but again we modify the stiffness, that's why it doesn't matter. So let's take out this one again. Alright, so I have those now. What else? Okay, so we did the sections. But now, yes.
For the leading column and rigid length, we have to set the on weight and mass to 0, or just
This is a different story. We'll do it in a while now. I'll show you. So, okay, so right now we have like members connected with rigid links, and everything is elastic, because pretty much every section is assigned this material, that's the default material, and this default material, it has like E and Fy. It will remain elastic. It's not a nonlinear material. And then we need to define, as we said, now the nonlinear springs, all the work that you have done in assignment number 3. So you need to define those nonlinear springs. So okay, so if I go here and then we need to start defining our plastic hinge. So what we do, again, we go to define and then we assign. So I go to define and I go to section, and then I go to the last one here, which is hinge properties, and I select this one, and then I say add new property. So it says, okay, what's the default? Okay, I'll use steel. So it tell me, okay, give it a name. Okay, for like just to make it like quicker again, I'll just assume one plastic hinge, one nonlinear hinge to define one nonlinear hinge for all the columns, and one for all the beams. Of course, you have different ones, right? But just I'll assume the same, assuming I have the same section, which is not correct, but anyway. So let's call it like column column hinge. And then it tells me, okay, what's the hinge type? Is it force controlled, brittle, or deformation control, ductile? Which type are you using? Ductile, deformation control, because I have capping and then I go down and so on. So it's not force control, okay? Because force control means at one point I break, so I don't go down. So deformation control. And it tells me, okay, what are you trying this hinge? Like, it's modeling what? It's modeling axial load with deformation. Maybe if you have like a brace or something. Is it modeling like shear in X, shear in Y? Is modeling torsion, My, M2? Is it modeling like interacting PM? So what are we trying to model here? Moment, right? Which is M3. So you will say, okay, ideally we should go like to PM to account for the force. Yeah, ideally, which you can do, but the problem here, like in SAP, like if you use like this type of models right now, you will run into like a convergence problem when you try to solve. Okay, particularly when you are doing like response history analysis. So that's why we'll stay away from those ones, and we'll stick for now with M3 only. So I'll click on M3, which is MX pretty much. And then once I click, okay, so now it gives me like this dialog box that I need to define. So as you see, if you look at this figure right here, and then you see, okay, now I have my backbone curve and I need to start defining like those points, the ones that you have defined in assignment number 3. Yeah, a quick point, like if you did, like after you saw the solution, like the suggested solution that I posted, okay, if you have values that are different, that's fine. If you did something like a big mistake, let's say like theta p should be like 3%, you calculated it 3.5, that's fine. But if you did it like 30%, so you did like something like a big mistake, then you have to modify before you go into assignment number 4, because otherwise you will get things like that doesn't make sense. So we need like, okay, variability between each of you, but still like nothing like so if you found like you did a mistake with the modeling, something substantial, then you can modify, that's fine. All right, so let's see what we're trying to define, because I have like many checkboxes and like things like this and radio buttons. So let's see what I'm trying to model. So I'm trying to model a type moment rotation for like reinforced concrete and so on. They sometimes like model moment curvature instead. Anyway, here for steel we are modeling moment rotation. The hysteresis type, okay, it's isotropic, okay, for now. Here I need to start defining like those points. So I have like A, B, C, D, E, positive direction and negative direction. I have it selected here at symmetric, assuming that I don't consider the composite action for this model, so it's symmetric. If not, then I release this one, then I need to define also the negative side. So okay, symmetric. I come here and it says, okay, after point E, which is the last point in your backbone, what do you want me to do? Do you want me to extrapolate, meaning I keep going with the residual, or do you want me to drop to 0? So we'll say drop to 0, assuming I have a theta ultimate that's associated with like any type of fracture or something. So drop to 0. So now for this one, the scaling for moment, I don't want it to calculate the moment, the yield moment, and the yield rotation based on the section I input. I can do that. But just to be safe, I'll take out those checkboxes, and then I will need to specify exactly what's the values for the my, which is point B, the magenta one. I need to specify my, I need to specify theta y. And then everything defined in this backbone curve will be with respect to my and theta y. So all right, and we are now doing the columns. So W24 by 146. Anybody has MY? Can do it quickly? No? Okay, let me do it myself. Okay, so W24 by 146. Okay, it's already here. So MY is around okay, it's around like, let's say 20,000. 20,000 keep inch. So this is MY, or MY effective, 1.1 FY expected multiplied by Z, right? Rotation, okay, so this is based again on your backbone and the stiffness. I have the stiffness, I have MY, calculate theta Y. Let's say it's, can anybody suggest a number? Now that you have some sense of numbers, can you say at what rotation I'm expecting a column to yield? Two percent, 1%, 0.1%, 0.5%, 0.2, 0.5. Let's go with 0.5, which is okay, similar to the assignment and the midterm. So yeah, around 0.5%. Oh, of course, it depends on a lot of parameters, the stiffness and the section itself, but more or less, okay, it's around 0.5%. So 0.005, right? And then you have this acceptance criteria, which we don't care about for the moment, but then you can define the acceptance criteria if you remember, like ASC 41, the other side of the table, if you need to define those ones, because later after you run the pushover, it will show you colors and it will show you at which point in your pushover you hit this criteria. So if you defined those correctly, you can do this, but this is not the scope of the course. Okay, so I defined those, MY and theta Y, and then I need to come here and then start adding those values. In this one, I have MY, I have theta Y. So in this backbone, I'm actually modeling plastic rotation. That's why, like, if you look here at this point, it already says, like, the origin point 0 and 0. And then point B, in the magenta color over here, it says 1, which is the ratio of this moment to this MY. And then the other point is 0, and then you can't modify this one, because this is plastic, right? So at MY, I don't have any plastic. Okay? So that's why it's 0. Then I go to point C. So how much it should be point C with respect to point B for moment? 1.1, okay. If you want something else, if you have any other justification for something else, you can use it. How much is this rotation at this point C with respect to theta Y? Okay, so then you have theta P, right? Or if you are using ASC 41, you already have the value, because it's, if you remember, the A parameter, which is given like 6 theta Y or 9 theta Y or so on. If you are doing ATC 72-1, then you have theta P. Then if you want to get this value, how much is it with respect to theta Y? Okay, so you have theta P, you add theta Y, and then you divide by theta Y. And then you get how much is more. Correct? So you do this one, and then let's assume it's like, I don't know, 8 or something. Then you see the figure, it's already modified. The next point, point D, which is associated with the residual, right? So you need to say, okay, this point D, how much is the moment at this point? So I don't know, if you're using point 2, if you're using point 4, you use whatever you want to use, and then I put point 4. How much is the rotation at this one? Again, you can calculate this one using theta PC and so on, and then you divide. And then let's say like this one, for example, like 26 times theta y. Point E, the same, it will have the same residual, 0.4. And I will like fracture or whatever, or I will drop to 0 at what point? I have 0.5%. So I don't know. Let's say like 20% or something rotation, which is like 40 times more, right? So I can put like 40. So like I'm saying, like I will lose like my strength completely due to fracture or something at 20% drift, and 20% drift divided by 0.5% drift, it's 40 times. That's why I put 40 here. So now I look at my backbone curve and it makes sense. Any questions?
Just for the acceptance criteria, is there one for the ATC?
For the no. No. Okay, because you have like special documents like related to the acceptance criteria. All right. For the ATC, no. So it will refer you again to the ASC 41 or the FEMA 356. All right, so that's it. I defined everything. Okay. Any questions?
Is it possible to modify point B? The rotation is already 0. Like I can't modify it.
But why do you need to modify?
Because we have theta y corresponding to my.
Yes.
So it's not. It must add a number, not 0.
Well, the number is here.
Okay. But based on FEMA, I think the corresponding theta y is my, right? So we have
Well, okay.
an opposite.
I have this point for the backbone. It's always there. So at any my, I have corresponding theta y. At this point, I don't have any plastic rotation. So for any type of backbone you are using, for sure I have this part with 0 plastic rotation. So in no way it will go like this from the beginning. For any type of backbone, there is an elastic part. So it has to be like this. ASC or ATC or any other thing. So you need to have this kind of thing. All right?
This residual
Mm-hmm.
rotation or strength, you kind of talked about not randomly picking it, but kind of educated.
0.4?
Yeah.
0.4.
Yeah.
Okay.
In my graph, in my assignment, I just drew the curve all the way down without the residual because I wasn't sure.
Okay. No. You can do this. Okay. Again, it's up to you. You want to assume there is no residual? It's up to you. For this assignment, it's up to you. You have some modeling recommendations, you have the references, and the references tell you, okay, add this type of residual. If you don't want to add it, it's up to you. So again, this is in your assumptions. So based on my experience, I say, okay, you have like some residual. Maybe if you are not very comfortable like with 0.4, a little bit too much, you can use 0.2, you can use 0.1. If you want to ignore it, again, it's up to you. For assignment number 4, it's up to you. Okay? All right, so, okay, I've done with this one. Okay. So column hinge. So now let's do a new one for the beams. Again, steel, the same, let's call it beam hinge. Again, M3, I'm trying to model. So again, the same things. So now we said it's a W21 by 57. So assuming I have a reduced beam section, maybe I don't have a reduced beam section. Okay, assuming I have a reduced beam section. So for this type of section with reduced beam section, I have around 4500 kip inch. So 4500 kip inch. For the theta, again we can use the same value. It should be a little bit more flexible. We can use 0.07 or 6. It doesn't matter. Okay, let's use 7. Doesn't matter. Okay, or let's make it 5, so I have the same for everyone. What else? Then I need again to define those. So again, I'll use the same 1.1. If you want to use different, again, up to you. 0.4. 0.4. This one, maybe it's a little bit flexible. So maybe I go to, what was the previous one? 8? Okay, so you can go like a 10 maybe. For this one, let's go like, it doesn't matter, any number. And then this is like, I'm just putting numbers, it doesn't matter for now. So I defined, that's it, another one for the beam, for the RBS with the reduced moment. And then I say, okay. So now I have the 2 hinges, and then I need to assign. I defined, then I need to assign. So, okay. Then let's go for the columns. So for the columns, I need to assign the hinges at the start and at the end. So I select those. Here you go. Let's leave this one because this one it's already broken into 2 pieces. So I'll go to the top one. And then I go to assign frame hinges over here. And then it will tell me, okay, what's the hinge property you are using? So I'm using this column hinge, the one I just defined. It will tell me where do you want to add this hinge relative to the length of the member. So I want to put it at 0 at the start, and I say add hinge. And I want to put it at 1 at the end, add hinge. Of course, in my model here, I'm not considering the panel zone, right? I'm not considering the panel zone because I'm modeling like center line dimension. If I have the panel zone, it's a little bit longer story because I have to break this one here, and then I put, if you remember the parallelogram model, I need to have like small members over here, rigid members with like some kind of spring. So it will take more time if you want to include it. So for now, I just excluded this one. So I have at point at relative distance 0, at relative distance 1. That's it. Okay. So now it shows you it's looks similar to the release, and then it says here like, okay, this is column hinge. I give it like some kind of notation. So it says this one is hinge 1H1. The one at the top is like 4H2. So I think they name it like based on the grid they created automatically. So let's do the same for those 2 members. So I select the bottom part. Again, I should have like 2 types of column hinges because I have different sections, but just for now. So I select the bottom part. Again, I say assign frame section, frame hinges. And this one, I need to do it at the start of the column. So here, not at the end. So at 0, add hinge, okay. I select the top part again, and I say assign frame hinges at 1 at the end over here. So add hinge, okay. Okay. So now I select all the beams. The same process, assign frame hinges, and this one I'm using the beam hinge. So where do we want to put this hinge for the beams? At the end and at the beginning? No.
0.109.
Because we said like the RBS is not at the end. It's at a given value. So you already did this like in your assignment. So if I have the column like this, and I have the center line, and I have the beam, and I have the RBS rotation somewhere here. Like if I look in the plan view, it's something like this. So I have the depth of the column. So from this point, I need to measure this distance to the center of the RBS. So how much is x? So you have this parameter a, right? Which is, I don't know, like 0.6 something d or something, I don't remember, of the depth of the beam. So you have this parameter a, and then you add half the depth of the column, then you have this value. Now, when you have this value x, you divide it by the length of the beam, center line to center line, then you will get this value that we need to put here, which is not 0, it will be a little bit more. How much did you say, John?
0.1.
0.1? Okay, so he says 0.1. So 0.1, and the other one will be 0.9, right? Okay, so that's it. So technically here I have like I have this plastic hinge over here, and then this is the elastic member, and here there is another elastic member, and I have a plastic hinge. Okay. So that's it. So now I'm done with the sections. So next part, let's assign loads. Let's assign loads. Okay. Well, actually, the first step, like before, what we did, like first to save, right? Okay, because this is the last thing you need to do. Like something crashes and that's it. And save it like many times, because again, like sometimes with SAP, like you save it and then it doesn't open again. So just to be safe. Anyway, so let's save it. So I'll just save. Actually, I have. Let's call it. Okay, so I save it. And then. Okay, and then we said like let's define the loads, right? So in your assignment, you are given the loads, and you don't have any load cases. You just, it says like use all those loads, like something like pound per square foot and pound per linear foot. So you need to transfer all those values, the tributary area and half the area, and get the PP delta and the PT or the tributary load, and then you need to assign. You don't have live load and dead load and some kind of combinations, which is typically the way to do it. You are just given all the loads, and then you are said, okay, just sum up, multiply by the area, and so on. But you have to be careful, because like some loads are given pound per square foot, PSF, and other are like pound LF per linear foot. So like weight of beams or columns per linear foot. For like area loads per square foot. It's okay. Anyway, so I go to define, and I define a load pattern. So you have the default, which is dead load, it's called. So let's delete this one. Or let's call it, like, let's leave it dead load, but let's call it gravity. Now for the thing that you have been saying, okay, so I have the loads already takes in consideration the weight of the elements. So if you don't want to duplicate like this calculation, then you need to take out the self weight. So instead of like modifying each section like the mass and the weight, I come here and then I say the self-weight multiplier is 0. Instead of modifying this one in the set modifier dialog when we modified the area, so I can do it here. So I won't duplicate again like the weight of the members again when I'm calculating this.
You can leave it without assigning it or do it.
You can, but again, like, because for this assignment you are given specific values, okay, which could be taking in consideration like some kind of splices in between, like some kind of other material that you are not considering here. So to be safe, use the ones you're given and set everything default here to 0. Again, up to you. So I define this one, gravity, okay. Actually, since we are here, let's define again another load pattern that we are going to use later, which is for the pushover. Or actually, let's do it later, it doesn't matter. Okay, so we define this one, and then I need to start assigning the loads. So I need to select all those points, the grid points, and I need to come here and say assign joint load forces. The load pattern is gravity, coordinate system global, and I want a force in the global z direction, something that was acting here. How much is it? Okay, so you have to calculate and then you come up with some value in kips. So it's like around 40 kip, negative, going down. And then I say okay. Okay, so I have those ones I need to take out because I selected the splice. So you can select and then assign joint load forces. Let's make those ones 0 and replace. Okay. So I applied the values, and then again I need to apply the P delta forces now on the leaning column. So I come here and I select the nodes. I say assign joint loads forces, again gravity. How much is it? Okay, it should be much more. This is the P delta, so it will be something in the magnitude of like 400, 500, 600 kips. So like it's 100 times more. Okay, it depends on the geometry, of course, but for this example, let's use like 500. Again, negative. Okay, that's why like we made the section really axially rigid, so it won't deform too much. So that's it for the loads. I need to assign masses. Why do I need to assign mass? You are not doing nonlinear analysis. You are not doing dynamic analysis. So why do we need masses? Because we are doing pushover. And for pushover, we need to push with the load pattern. And pretty much what we are going to do today, we are going to push with the first mode. So meaning, if the software will push with the first mode, the software need to know the first mode. It need to be able to calculate the first mode pattern. So in order to calculate the first mode pattern, it need to solve the eigenvalue problem. And to solve the eigenvalue problem, I need to have two things correct: stiffness and mass. Actually, this is the most important part of your solution, because given the period that you will get, you can know, like, do you have any problem in your model or no? You do this one and then you get a period of 1 second. Is it correct or wrong or right? It's okay. Yeah, I did like a trick question. Okay, yeah, 1 second is fine. It should be like 1.5 moment frame. 10 seconds doesn't make sense. 10 seconds and more, this is like what you expect like from bridges, like long span bridges, 10, 20. So yeah, it should be like something in this range. So 1 second or so on. So you can know if you have a problem in your model. So if you have something wrong, then maybe you assigned the wrong mass, wrong value, or you have something more substantial, you assigned something, the stiffness is really wrong. Anyway, so let's assign the masses. This is easy. Again, let's select those points. Only the ones for the frame. The mass, how do you calculate the mass? Again, if I look at the plan view, you have system here, system here. I'm looking in this direction. I have the loads acting, because I'm modeling this one. So I have the loads here. All the loads, tributary, everything, and P delta. And then if you take the load, how do you transform it into mass? How you transform moment force to mass? Divided by acceleration. MA, right? F equal to MA. F being the weight. So W is equal to MA. And the acceleration in our case is G. Well, 9 if we are working metric. We are working imperial. So it will be 38 something inch square per second, right? What?
386?
Yeah, I don't remember the exact, but yeah, 38 something. So inch square per second, not 10. So you have this load, you divide it by G, same units, and then you got your mass, then you divide it by 4 nodes. I don't need the leading column here, okay? So we divide it by 4 nodes equally, it doesn't matter. Because the mass is only giving inertia, nothing else. Inertia forces. So I select again the nodes. I say assign it was joint, yeah, the first one, joint masses, all right? And then, okay, so as mass, because I will provide this one, the direction, global, in the global direction. So it says, okay, how much is the value? Okay, so let's assume it's something like 0.5, 0.4 or 0.45 kip mass, which is kip inch square, second square. So where do you want to apply it? Well, you can apply it in the 3 translational direction, it's fine. But pretty much later on, we are going to apply a ground motion in the 2D, in the X direction, right? So I only should assign a translation global X. If you are doing a 3D model, and then the ground motion has 3 components, 2 orthogonal, horizontal, and 1 vertical, then I need to assign this inertia, this mass, to the 3 global directions. But for here, I can just put it here, 0.45, or if we are not losing anything, you can put it for all of them, it doesn't matter. And then if you use it, use it. If you don't use it, doesn't matter. Okay? This means like this mass that will be excited when I have a translation in this direction. Okay? Okay. So that's it. So now I have them. And final step is to define the pushover, right? So I say define load pattern, and this one I'll call it pushover. The type, actually no, not from here, sorry, cancel. I go to define its load cases. So those are like the ones that the load cases that will run like in default. This dead load, let's delete it. I don't need this one. Model, okay, we'll need the model because this one will get me the model shapes that I will use. So I add a new case. Now this one, I'll call it pushover. Load case type, so is it static, model, time history when you later on for assignment 5, when you are doing time history. So you need to select time history, and then you need to select the file for the ground motion. So here I'm doing static. It's called nonlinear static. So it is static and it is nonlinear, and P delta, of course. You can say P delta plus large displacement, but you don't need it. You will lose time in computation, but you don't need it in this case. And then, okay, you need to define like the load type, the pattern, which is we are going to use the mode shape. Which mode? Mode number 1, scaled 1, and then I need to add it. But before I do this, there is a step I forgot. I need to define a load case for the gravity, right? I need to define first the load case, because we defined the load pattern for the gravity, but not the load case. So let me go back and define load case. Let's delete the dead load. It is dead, and add a new one. We call it gravity. And this one, pretty much, it's a gravity. This one, add from this load pattern. And it's nonlinear with P delta, again, static. All right? So I defined the load pattern, and then I defined a load case for the gravity. That's it. And then I define a new load case, which is the pushover, we said. And this one, again, static, nonlinear, P delta. But you have to be careful. Initial conditions for the gravity will start from 0, because this is the first step. We apply gravity. But then for the pushover, I need to continue not from 0. I need to go from the end of the gravity. After I apply the gravity, I start pushing. So for this one, I go continue from state at end of nonlinear case. Which nonlinear case? The gravity. Load pattern, we said we are going to use the mode load pattern. Number 1, add. Then I need to define some other parameters here that are important for this load case, which is how do you apply the load, how the results are saved, how the pushover is solved. So let's go with the load application. Is it displacement control or load control? Displacement control. We are going to use a monitor displacement, meaning I'm going to keep pushing until some displacement reach a given value. For this one, I monitor something on the roof, let's say this point, until it's pushed given amount. So how much? You can push like up to 10% roof drift, 5% roof drift, it's up to you. Let's say we want to push to 10% roof drift, this point. So the value we are going to push, if I have like here 144 inches multiplied by 4, so this is something like 600 inches. So 10% of that is 60, right? So I push to 60. What are you going to push to 60? What's the monitor displacement? I'm monitoring U1, which is in the X direction. This is U1. Which joint? So you need to look up the number of the joint. But for this one, it's pretty much joint number 5. You can check later, but it's joint number 5. That's why it's selected automatically here, because they know. If you want to modify something else, it's fine. So 0.5, okay. Result saved, modify. So are you going to save the final state after you're done with the pushover, just the final value, or everything? Everything, because we need to plot the whole curve. So multiple states. How many? You are pushing like 60 inches. So maybe you do it like 50 steps. Each step like 1 inch push. If you want to be like have a better resolution in your curve, maybe use more points. It's up to you. So let's say 50 is the minimum and the maximum is 100. Okay. Nonlinear parameters. This one, okay. So again, this has to do with the convergence. It's very important. You have lots of parameters. Most of the people they have no idea what's going on here. It's very important, particularly when you are solving nonlinear response history analysis. you need to play with those numbers in order to make conversions happen. So you tell it like when you are doing some kind of trials and iterations, like to reach conversions, how many steps do you say? Like it says like here, like I don't know, 200, or it says like the tolerance is like 10 to the power negative 4. So maybe if I want to converge easier, maybe I need to relax this value, make it a little bit higher, not very small. And maybe I need to increase the number of iterations. But at one point, it doesn't make sense. So you don't come and say, okay, that's very good. Let's go here and make it like 40,000. Okay, this has to do with like numerical methods. If you have some kind of background with the type of solution of differential equations or nonlinear equations in general, the Newton-Raphson, the secant method, like the bisection, all those type of things, you'll find that there is some sense of the number of iteration and the tolerance. Beyond this limit, the methods that you are using, it won't converge anyway. So those who will not play with those right now, we'll leave them, because this pushover, you won't have any problem with converging. But for nonlinear response history analysis, if you are having a strong ground shaking, strong nonlinear behavior, you need to play with those in order to converge. And even in SAP, you won't, sometimes if you have really strong ground motion, you won't converge. That's why OpenCs and all those kind of programs are better, because you can play like with much more options, use those things. Okay, you can really go into detail. This is the most important part. Like here, you need to select this one. Very important. Otherwise, it will be wrong. So this one, it says like how do you apply the loads. So the first one, it says, okay, you upload, let's say for step 1, and then the hinge is loaded. And then before it goes to step 2, it should stop here and then keep going. So if you select the first one, it will go back to 0, and then go all the way to step 2, which we don't want to do. The last one, again, it's the same, but it will go back to step 0, and then it will push to step 2, using a modified stiffness, which again we don't want to do. We need to do this one with a local distribution. So you keep pushing, it has the values. Then keep pushing, have the values. Keep pushing, and so on.
Why do we want one over the other?
For this one?
Yeah.
Well, it depends on the type of analysis that you are going to do, like for reinforced concrete and so on. Sometimes they do like this kind of thing. So instead of using, like if they are not very comfortable with like the initial stiffness, like 40% and 80%, so sometimes they push to the first point, and it's something called like it's like a predictor, corrector. So it goes to the future, it sees what's happening, and then it goes back and then modify before it goes to the second step. So this is what's going to happen for those two. So it goes to the future. This is what happens. Okay, I'll go back, and then I modify, and then I go to the next step. And then I go to step number 2. This is what happens. I go back, and before I go to step 3, I modify. For some cases, they use it. For us, the pushover that we do, we just use this one. We keep going. Okay. So, okay. And then that's it. Done. So now it's done. Okay, now we need to run. So before I run, I need to set the analysis option. Very important step again, because now we have some things in X and Y direction in 3D, even though we have a 2D model, but the forces and like the masses, some things are in the other direction also. So to make sure we are analyzing everything in the 2D, because I don't have a support system in the other direction. So you come here and you say, I'm doing, this one, an XZ plane. Okay, so you select this one in the analysis option. Okay, and then you run. So I'm running model, gravity, and pushover. Okay, so now I have the one that it shows right now. It shows the model load case, and it tells me T, the period. This is where you know if you are right or wrong. It's 1.49, which is fine. You have something weird, then you need to check your mode. So this is the first mode, and this is pretty much what I expected it to be. The first mode for like moment frames, it's more or less like something linear like this. Maybe it doesn't look very linear because we didn't assign the hinges correctly. I assumed the same hinge for all the columns, but if I did it correctly, it will be more or less linear. If I want to explore more, this is the second mode. So this is the eigenvector. It's 0.4. If I go to the third, I start getting like a little bit more weird and like less probable to happen. And if I keep going, it doesn't matter. So I don't need all of those. I just need the first one pretty much. Okay, so this is the model analysis. Let's go to the gravity. If I go to the gravity, okay, so this is what happens. If I look at the gravity, so it's like those columns are shortened. Okay, there is exaggeration, of course, but because those ones, the members are actual members, and the forces, the loads are actual forces, so I have some elastic deformation. Those ones, even though they have like very large forces, they didn't move because they are very rigid. Therefore, we did it correctly. If you see those like squashed, then you didn't make them rigid enough. Like if you can go here and then you can see, okay, this is like 0.05 inches, very small, U3. If you divide the force by the area, you can get the stress. You divide it by E, you can get the strain, which is pretty much multiplied by L. You get how much shorting if you want to check. Let's go to the one we care about, like the pushover right now. So step number 1, doesn't, okay. So this is step 1, very, very small at the beginning, like 1.2 inches. If I keep going, step 2, step 3, step 4, now I'm starting getting this. So first I reached like this damage state, but I don't care for those, but pretty much like I reached this point. So plastic hinging in these beams. Then I got plastic hinging in the others. I keep going. Then I got in the columns at the base. I keep going. Now, the lateral drift is keeping increasing, but you see it like going back. It doesn't mean it's less. It's still more, but it's just because it's adjusting the view. So this point is keep moving. Okay. So I keep going again, and now I have something like a mechanism that will be pushed more and so on. So using those ones, I can know like if I have like some acceptance criteria. If I do the animation, so this is what happens, okay? It's going like left and right. Of course, it's going in one direction, but like for SAP, it do it like this. Anyway, okay, I need to see the pushover curve, right? So if I go to display, show, here you go, show static pushover curve, pretty easy. So I go to this one, here you go. So now I have my pushover. So it tells me, okay, at one point, here I reached the capping at around like, I don't know, 10 inches. You can say 10 inches divided by how much is the height. You see how much percent drift, like root drift. And then I go down like this, right away. I don't have any hardening. And then at one point, again, I have another thing, and then I didn't push all the way. No, actually, it went all the way up to 60 inches. But sometimes it could stop before. For conversions, maybe it can stop before. It doesn't matter. Like up to here, I already characterized like most of my curve. If you want to save it because you need to plot it for your assignment and so on, you can go to File, and then Display Tables, and then you get Displacement, Base Shear Force. You can do the same. You can look at those columns here at the base. You can look at the reactions at those 4 points. the reaction in this direction, the shear force, you can sum it up, and then you do the same plus the shear force at this point for the leading column, and then you sum it up, and then you plot the two. So one will give you V P delta, the pushover curve with P delta, and the other one without P delta. The one we already saw, it's already taking into consideration all of the shear force and the phase. And of course, you need to normalize. So the pushover curve that we have shown, it's in kips. You need to divide it by the seismic weight. So it will be something like 0.2 or so on. If you want to look at something else, like look more, show hinge results. So here, let's look at like 1H1. If you remember, like this is like the hinge here, this one. So yeah, it elastic, and then I had plastification, right? At the base. If I look at the top, I don't remember what's the name, maybe 1H2. So it remained elastic. So the columns remained elastic all over, except for the base. If I look at the beams, so again, of course you need to move like a little bit. And then you can see at which point like you reach like any given performance state. So you need to do those. You need to get out again the values for the displacement at each floor. You need to calculate the drift at each story. You need to plot the profiles for the drifts, the profiles for the displacement. You need to report back in this Excel sheet, and you have to be very, very careful when you are reporting those values. You need to report the shear forces. You have the shear force, you multiply by the height, you get the moment. So if you have the total shear force here, it's like 200 kips, you multiply it by h, you get the moment. You do the same here, multiply it by h, you get the moment, and then you report those values back, or you plot them. So again, I don't have actually the time, like there are, so you need to do all of those things, and then, but it's up to you. You need to do it, you need, but like SAP is well documented. Like if you go to like YouTube and so on, like you'll find lots of videos. If you say, okay, how do I extract the shear forces or the reactions from my model, it will tell you what to do. So those things you need to do it yourself. And then you need to report the things discussed in assignment 4. So this is for pushover. Okay, any questions? No questions at all?
If we want to not consider the PZ, right? So we have to set the initial pushover to 0, right? Because we start from at the end of the graph.
You don't want to include the P delta?
Yes.
If you don't want to include it, don't model the leading column. Or actually model the leading column, but just sum up those shear forces.
Suppose you want to incorporate effect due to gravity frames and...
If you're including the effect of the gravity frame, then you will do the equivalent gravity frame. So you will have another bay over here. And then for this bay, you will need to include, similar to what we did in the main frame. You will need to include like nonlinear springs for the beams and the column, and those ones you need to assign the backbone curve for the shear connection.
It's an equivalent frame. How do we assign it for a...
Sorry?
It's an equivalent frame, right?
All right.
How would you... What section properties would you take to get this frame?
We discussed this when we discussed the gravity frame. For the beam, it will be sigma IB or sigma Z. So you have to sum up. You see how many gravity beams you have?
How do you get the theta? Do we include a spring or... Like
You have to include spring.
How do you get theta P and theta BC for equivalent gravity?
This is if you look at the slides, those are given. Like how much is theta p, how much moment you have. If you have the composite action, it's like 40% of MP of the beam. And then at one point, if you remember, you have the bolt slip, and at one point you have like fracture, and at one point you have something. So if you look at the backbone curve, the slides, you have all the values, the recommended values for defining the backbone for beams as part of shear tap connections. All right. Be careful when you are solving assignment 4 again. What's given, like draw this figure, so you need to draw everything as it asks. And most importantly, for the Excel file, make sure like you have to report everything in keep inches. You have to report the values, because then I will take those Excel files and then I run some type of algorithm to process all those things and then do some plots. So if you have some error, okay.
If you want to model the panel from how we can connect the beam and the columns to the members.
No, it's okay. It will be I have like this is the column, and then I have like something like this. I have a node here, and then another element, another element, another element. Then I have here just a node connected fixed. Yeah, well, fixed. I have the hinge, the nonlinear spring, but yeah, and those are rigid ones with the releases at the end. And then I put here spring. Okay, so now you can model, now you can run, and now you can get the pushover curve. On Wednesday, we'll explain the last part of assignment 4, which says like something related to the target displacement. This we'll discuss on Wednesday. Thank you.